Welcome to lecture. We'll get started in just a minute or two, picking up where we left off, which should be right around here. And again, reminder, if you do have questions, feel free to ask them. We are going to pick up sort of where we left off. So really the next thing we're going to do is sort of name these guys. So if you want to sort of get a jump on that and kind of working through the names of these guys, we'll talk about it in just a minute or two. So give the name for these three molecules that we see up here on the screen. So we have 1, 2, and although they kind of look like they run together, they are separated, and 3. So again, why don't you take a couple minutes or so and then work through those and see what you come up with, and we will talk about it. So again, if you're just joining, we're continuing on with our talk of alkanes. So right now, work on these 3 here, and then we will obviously talk about it in a minute or 2. So give the IUPAC name for these guys as you see on the screen. So again, if you just came in, we are working on these examples that we see on the screen. Please give the names to those. And in probably about a minute or so, we will start going through them, make sure everybody's on the same page. All right, so why don't we take a look at these and kind of go through them and kind of review what we talked about last time in terms of how to sort of properly name these guys. Again, when we name them, we do go with sort of the IUPAC naming. That's almost like the sort of official way of naming them. Remember that when you start, you really want to just go with the longest continuous carbon chain. That's basically where you always sort of want to start. Again, it doesn't matter. It doesn't necessarily have to be the straightest. It could go up, it could go down. The only thing is, once you start one direction, you can't go back over the same direction. So you go from one end to the other until you hit a dead end. So if we look at the top one, number one up here, if we go just left to right, we have 1, 2, 3, 4, 5, and 6 straight across. If we start left and then go upwards, we have 1, 2, 3, 4, and 5, which is obviously less than 6. If we start at the left and go to the second upward one, 1, 2, 3, 4, 5, and then go up 6. And then obviously, if we start at the up and come down and then up again, so 1, 2, 3, 4, 5, 6, kind of making a U-shaped, going up and then coming down and going back up. You can see no matter sort of which way you go, it looks like 6 is our longest continuous chain. Good idea, usually just to take the straightest one here. So we'll just take that one. Again, 6 carbons. Everything is based off of those alkane names that we talked about last time. So the base of our name should be hexane. Again, they're all single bonded, so it should be hexane. We then have, off of that main chain, like we talked about as well, we have what are referred to as groups. So over here we have a 1 carbon group. Remember, also based off of those alkanes, except the groups end in YL, so it goes from methane to a methyl group, again YL. Over here we have a 2 carbon group. Again, the 2 carbon is going to be based off of ethane, but because it's a group, as we talked about last time, it has 1 less hydrogen that allows it to connect. It will be known as a ethyl group. So these are the 2 groups that we have attached to that 6 carbon chain. Now, as we also talked about, once you've sort of identified everything, you then want to number the chains. So you have 2 options. You could start over here, each of the carbons in the longest chain. That'd be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. And if we go in the orange direction, we will have groups at carbon number 3 and carbon number 5. Now, if we number it in our other option, which would be going right to left, we number it right to left. This is going to be carbon 1. This is going to be carbon 2. This is going to be carbon 3, carbon 4, carbon 5, and carbon 6. So going sort of the bluish color, we would have groups at carbon number 2 and carbon number 4. Remember that when we are choosing which way to go, we always want the smallest. So in organic chemistry, it's always the smallest, which is important. So in this case, we want to give those groups the smallest numbering. So we will number in this direction. And that means at carbon number 2, I have a methyl group. At carbon number 4, I have an ethyl group. Remember as well that we talked about last time, in between a number and a letter, you put the dash. In between 2 numbers, you put a comma. And the last thing is, when we do put these groups on, we do want to do it in alphabetical order. Alphabetical order regardless of number. So even though this guy, the ethyl, has a higher number alphabetically, E comes before M. So that would come first. So this would be putting it all together. 4 ethyl, ethyl dash 2 methyl hexane. So 4 ethyl, 2 methyl hexane. Any questions on that name there? Okay, and again, if you do have questions, feel free to type them. I will come back to them if I moved on. Guy on the bottom left here, we're going to count. We got 1, 2, 3, 4, 5, 6, and 7. We also would have 1, 2, 3, 4 if we went down and to the right. If we started at the top and went down and to the left and then down, 1, 2, 3, 4, 5, 6. So it looks like our longest continuous carbon chain, even though it's drawn downward there, is this guy here. And that is going to be 1, 2, 3, 4, 5, 6, 7 carbons. Again, 7 carbons means the base of our name should be heptane for our 7 carbons. In this particular case, we have just one group that is hanging off of there. Also a 1 carbon group, which is going to be our methyl group. So in this case, we want to again number whichever way gives us the smaller number. So always the smaller number. So if we go left to right, bottom left up, that gives us 1, 2, 3, 4, 5, where that methyl would be. If we numbered the other way, 1, 2, 3, 4, 5, 6, and 7. That means going the green way here, our methyl group is at carbon number 3, which is smaller than going the opposite way, where this would be carbon 1, 2, 3, 4, and 5. So again, that's going to give us a bigger number going in this direction. So we want the smaller number. So that means we have 3 methyl heptane. Any questions on that one? And lastly, if you got to this guy over here, the longest carbon chain, let's take a looky. So we got, let's put dots here. 1, 2, 3, 4, 5, 6, if you go straight. If we go this way with maybe red dots, 1, 2, 3, 4, 5, 6, and 7. That's looking promising. Now, if we have some more options here, so if we go with, say, starting up here, this would be 1, this would be 2, this would be 3, this would be 4, this would be 5, this would be 6, this would be 7, and that would be 8. The longest carbon chain, as illustrated here, is actually 8. And again, it is not the straightest, but it is the longest continuous chain that comes about this way. So again, you want to make sure that you count sort of all your options in terms of which way to get the longest carbon chain. It may, again, not always be that straightest. So 8 carbons here. Going to give us a base name of octane. Now, when we look at it over here, we have a 1 carbon group, which is our methyl group. We have over here a 2 carbon group, which is our ethyl group. So again, we want to number it in whichever way will give those groups the smaller numbers. So if we go in this direction, using green, 1, 2, 3, 4, 5, 6, 7, and 8. That will give us groups at carbon number 3 and carbon number 5. And if we number sort of the other way, let's see if it makes a diff. Go with red. If we number in this other direction, this would be carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, carbon number 6, carbon number 7, and carbon number 8. Going in the red direction, we have a group at carbon number 4 and a group at carbon number 6. So again, you can see that this is going to give you a larger set of numbers. So we would want to go with our red way of numbering. And in that case, that means that At carbon number 3, we have a methyl group going the green direction. And at carbon number 5, we have our ethyl group. Same deal here, alphabetical, even though it has a larger number, it's going to come first. So that's going to give us 5 ethyl with the dash in between, dash 3 methyl as I run out of room. So I'm going to go above it there, methyl. And then obviously that should come together. I'll write the octane like this, octane. Just kind of get that out of the way. So 5 ethyl, 3 methyl, octane. Any questions on how to name these guys here? Okay. So let's see what we got going on here. Just get those. There's some more practice if you want. Let's do these guys here. If you like, in this case, what we want to draw is the condensed formula for each of these names. So why don't you give it a go, take a minute or two and draw the condensed formula. Again, the condensed formula meaning when you essentially don't draw out all the hydrogens, so like CH3, CH2. So take a minute or two and then we'll talk about drawing these. Okay, so let's take a look at some of these. Remember, as I mentioned last time, I think when you have the name and you want to draw it, It's sort of the easier of the two because it pretty much tells you what to do. Remember that when you have the name and you want to draw it, you always kind of want to work in that direction from the back of the name forward. So that's where we'll start here. So butane basically tells us that it has 4 carbons, and that's really all you want to kind of start with here to begin. You just want to place what's sometimes called the carbon skeleton, just the 4 carbons. I'm going to leave some rooms because I'm going to squeeze in some other letters there. And that takes care of the butane part. So that takes care of our 4 carbon part. Then again, at this point, you want to continue down the path. So we have dimethyl. So methyl, right, is a CH3 group. When we see the di, that means that there's not just one of those guys in the molecule, but there's actually 2 of them in the molecule. And they're located at carbons number 2 and 3 is essentially where that is. And because you are drawing it, you get to choose whichever way you want to number. If you want to number right to left, you can. Or you could go right or left to right. I'll get that right. There's a left side, a right side, I think, right? So I'm going to go left to right. So I'm going to just put a number here. I'm going to call that carbon number 1 right here, so you know. And I'm going to the right. So at carbon number 2, I should put my methyl group. It doesn't matter if you draw it up on that carbon or on the bottom of that carbon. And then at carbon number 3, I'm also going to draw my methyl group. Again, doesn't matter if you drew it up or down. That's going to take care of my dimethyl. Now, remember, the whole point of everything else is carbon needs to get to 4 bonds, and everything else is going to be hydrogen. So this guy at the end has only 1 line coming in, which means he needs 3 hydrogens. This carbon here has 1, 2, and 3 lines coming in, which means he just actually needs 1 hydrogen. The carbon to the left of him also has 1, 2, and 3 lines coming in, which means he will just make 1 more bond to hydrogen. And the guy at the end here has only 1 line coming in, which means he will need 3 hydrogens. So there you go. Any questions on that one there? All right, continuing on, again, working backwards. Heptane means 7. So that again, 1, 2, 3, 4, 5, 6, and 7, I think. There we go. And same deal here. We have an ethyl group. Again, ethyl based off of ethane, which is a 2 carbon group. Again, missing 1 hydrogen that allows it to connect in. Methyl, just like what we had above, a 1 carbon group based off of methane, also missing a hydrogen to allow it to come in. I am again going to go left to right, but you could go right to left. But I'm going to call again this guy over here carbon number 1, which means that carbon number 2, you could draw it on the bottom, but I will put it on top. We'll put our methyl group at carbon number 3. We will put our ethyl group. Remember that the connectivity does look like this. You shouldn't write it, go up here, like this. Because if you do, that implies that this carbon down here is connected to that carbon is connected to that carbon, then this carbon is connected to 3 other hydrogens, which technically speaking would give that carbon 2 main bonds. So you want to make sure you write it in that order. At that point, that takes care of everybody else. Again, everybody else here just going to be hydrogens, needs 3 at the end. This guy has 2 bonds, he needs 2, has 2 bonds, needs 2 hydrogens, 2 bonds, needs 2 hydrogens. This guy has 3 bonds, just 1 hydrogen, 3 bonds, 1 hydrogen, and 1 bond, 3 hydrogens there. Any questions on that one? And lastly, doing our same pattern, heading in this direction here. We got pentane, which is 5. So we'll start with our 5. Takes care of that. Working backwards at carbon number 4, we have a methyl group. Again, I'm going left to right. So that's carbon 1, 2, 3, and 4. Again, a methyl group being a CH3. Takes care of that part. And at carbon number 2, we have a chloral. Because I already chose left to right here, that means this has to be carbon number 2. Chloral is a chlorine group. So chloral is a chlorine, bromol would be a bromine group, fluoral would be a fluorine, iodo would be an iodine. Everybody else here going to be our hydrogens. So guy at the end needs 3, guy right here needs 1, guy in the middle needs 2, needs 1, and at the end here needs 3. So like I said before, I think drawing it from the name is really the easier of the two. Again, if you just work backwards, it pretty much tells you what to draw. And remember, to get everybody to 4 bonds, you just put the hydrogen in. Any questions on how to name these guys or draw them? Clearly, you need to be able to do so. You need to be able to draw these guys and name them. And as we mentioned last time, really everything based off of that first 10 alkanes. So you want to make sure, if you haven't done so already, you get a pretty good handle on those formulas and names, because everything goes back to them. All right. In organic chemistry, as we'll see as we go through these different chapters, there's a lot of different names that you'll come across. A lot of them are the IUPAC name, sort of the official type of name. But there's a lot of things that have sort of a generic name. There's a lot of things that have a common name, a name that, sort of historical is kept. So you will, as we go through these chapters, see a lot of different organic guys that essentially will have this same formula, but will have different names depending if it's IUPAC, common name, or so forth. So your question is, where's the CH2 bond? Let's go back real quick, take a look. So are you talking about, you're talking about like right here? How that kind of bonds in? Here. Right here. So just to draw it out for you, here we go. So hang on here. So for example, if we just take, I'll just take this section here. We'll just take this section of it. So basically what you have is this. If you kind of drew out all of the bonds, it all bonded like this. And this guy would have 2 hydrogens, which would be the CH2 right here. This guy would have 1 hydrogen, which would be the CH right here. This guy would have 2 hydrogens, which would be the CH2 right here. And this guy up here would be our 3 hydrogens. I didn't leave a lot of room. It's going to go at an angle, which would be our CH3 here. So that's sort of how they connect to each other. It's always the carbon connected to the carbon. Yeah, so this technically what we're doing here is the condensed version. So I would assume the condensed version should look like that. That's typically what it means, condensed version. This is really structural or expanded structural formula, as we talked about. So that's usually expanded structural formula. We draw out all the bonds. Again, we had our line structure, which kind of looks like that, if you remember. And this is typically the condensed formula, our structure. Some people call this the condensed structural formula because they put the little dashes in. Again, some people will just kind of minimize it just like this without the dashes, for example. And only show the dashes for the groups that are attached. So this is condensed formula. This is really condensed formula. I usually do it like this, to be honest with you, and most people probably will do it like this, but this technically, I guess, is condensed formula. But most people will include those little dashes. Most people will include those little dashes in between. And for the exam, you could do it this way. I think it's probably the best way. Yeah. Now, if he wants If he wants you to show the angles between the bonds, for us, you don't have to do that. Remember that the angles between these guys, are tetrahedral, and that's what gives it that zigzag shape. So, you know, I would follow the instructions from your lab instructor, so I don't want to tell you wrong. But for us, if you're asked to do the condensed formula just like that, it's perfectly fine. If they want you to show it, they'll sometimes have you do wedges and that type of stuff to sort of show the angles and stuff like between that, or draw the condensed formula like this. You know, that might be another way, I guess, maybe to show the angles, you know. I don't know, but for us in lecture, I'll just put it that way again. For lab, if she gave you some type of direction, do it that way. Or I guess if the video gave you some type of direction, do the lab that way. But for lecture or exams or something like that, if you're asked to draw the condensed formula, like we've been doing here, is perfectly fine. You don't have to show the angles or the bonds or anything like that. You should know that it is tetrahedral, and that's what gives it its zigzag shape. My guess is maybe they want you to do something like that up on top. But you don't have to include it for us. But again, for the lab portion, since I'm not the one with the pen or the electronic pen in these days, make sure you do it however you're sort of instructed to do it for those experiments, okay? All right. So continuing on, we talked about cycloalkanes last time. Remember, cycloalkanes are really just alkanes where yeah, so again, for me, just like I've been doing all these, yeah, this is perfectly fine for me, yeah, for us, for condensed formula. So just like that's perfect. So if I say draw the condensed formula, draw something like we've been doing, just like this. It's perfectly fine for me. You don't have to show any angles or anything like that, wedges or anything like that, okay? Again, for the lab, make sure you do it however they tell you if they give you instructions to do it, okay? All right, so cycloalkanes, as we talked about, are essentially basically alkanes, but the ends of them basically come together to make sort of a ring-type structure. These are usually our geometrical shapes. These are also usually the ones that we see a lot of times drawn in line structure. So remember that basically this would be the condensed version of this, as there's a carbon at each of those corners. And again, there would be technically 2 hydrogens at each of those corners. And that is 3 carbons, which is based off of propane. Again, because it's in that ring structure, we put cyclo in front of it. So this would be cyclopropane. This would be cyclobutane, as it has 1, 2, 3, and 4 carbons attached in a ring structure. It also has 2 less hydrogens than a straight chain. Again, that's because it loses those as it folds up on each other. So for example, if we had something attached to it, looks like that, for example, that's a single line badly drawn. Our main guy would be 1, 2, 3 carbons in a row, which is propane. Since it's in a ring, this would be cyclopropane. And remember, if you see a line drawn to the end, it's basically a methyl group at the end of it. So this would be methyl cyclopropane. So you would just kind of name it the group like normal. If you had more than one group, you would attach some numbers and do it alphabetical. Here's our cyclopentane and our cyclohexane here. So if we look at this guy, again, if we count our ring, we have 1, 2, 3, 4, 5, and 6 carbons. 6 carbons is based off of hexane. It's a ring structure here. So that makes it become cyclohexane because of that. And we would do the same approach. Here we have a methyl group attached. Here we have a ethyl group attached. And we would want to give the numbering here. And when we go to number this, we want to number it in a way that gives everybody the lowest set of numbers. So there's really sort of 2 options. We want to go 1, 2, 3, 4, 5, and 6. Alternatively, we could go the opposite way, 1, 2, 3, 4, 5, and 6, which would give us a larger number. So going this way gives us somebody at 1 and 2. If we started with this guy, 1, 2, 3, right? If we come this way, 1 for the methyl, this would be 1, 2, and 3, which would be 1 and 3, which is more. That's bad counting there. That's 1 and 3 each way. I'll learn to count as well. But if we go the opposite way, this is 1, 2, 3, 4, and 5, which obviously is more as well. So no matter which way we go, if we start at this guy and go this way, we get 1 and 3. If we start at this guy and go this way, we get 1 and 3. So the next thing you would want to look at is who's going to come first. And it's going to be this guy, right? Alphabetically. So we would want to give that guy the lower number. And in this case, it would be 1 ethyl, 3 methyl cyclohexane. And again here, because we started, I'm going to clean it up a little bit. We had a group here and a group here. We went 1, 2, and 3. Or if we started at this guy, 1, 2, and 3. Since they both gave us the same number, no matter which way we went, and those were the smallest set of numbers, the next thing that you would want to default to is alphabetical in terms of putting them together. And we would get that ethyl with the smaller number, which would give us 1 ethyl, 3 methyl cyclohexane. Any questions on that there? So if you just have one group like we had in the previous example I did, which looked like this, because there's only one group attached, it's assumed to be carbon number 1. And you don't necessarily need to give the number where it's at. So it's assumed wherever that is going to be carbon number 1. And that's why we just called this one methyl cyclopropane without the number, because it's assumed that group is carbon number 1. So only when you got multiple groups, you do have to give some numbers and their location of where those numbers would be. So here again, we can see we have just one group attached, so no number needed. We have our methyl group. This is our 6 carbon group, so that becomes cyclohexane. Again, it's assumed that this carbon right here is carbon number 1. Same thing here, we have one group attached. This is a 4 carbon group, and that 4 carbon group is based off of butane and becomes a butyl group. And our ring here is a 5-member ring, which is based off of pentane, but again, it's a ring, so that's cyclopentane. Again, no need for the number because it's the only group attached, so it's assumed to be carbon number 1. It's only when you have multiple groups attached that you do have to give a name. Only with one group on a cycloalkane, no name is necessary. So that's what this should say. Again, we want to give the lower number to our group. So here, if we look at this one here, we have a methyl group here. We also have another methyl group here. And that is where our dimethyl comes from. And they numbered 1, 2, 3. If you went the other way, starting at this guy, you would end up with the same numbers. And obviously, if you started here, I'll just go above it, and went this way, you would get a bigger number. So that is why they went 1 through 3, and that's where we give our numbers. Remember that even if they are the same group in that compound, you do have to give the number for each of those methyl groups. Even if they happen to be on the same carbon, you have to give the number twice, the same number twice. And again, this is a 6-member ring, so that is where we get our cyclohexane. So 1,3 dimethyl cyclohexane. Again, here you need to give each of those groups a number, and we want to go lowest set of numbers between the groups. If it's a tie, no matter which way you go, you get the same set of numbers like we had on the previous one. then you want to default to giving the one alphabetically the smaller number. So again, you want to keep kind of going until you get to the right sort of selection process. Alphabetical, lowest number, you know, you want to put those guys in the right order. So this would give us our 1-ethyl 3-methyl cyclohexane, which I think is what we had previously in this case. Again, this is really the same molecule as what we saw earlier. It's just turned around. Same idea here. If you number starting with this guy at a group, 1, 2, and 3, again, you would get the same number in terms of 1 and 3. But here, this is methyl, which starts with an M. This is ethyl, which starts with an E. So your next important thing is alphabetical, really. So we want to give our lower number to our alphabetical guy. And that's why, again, in this case, the ethyl would get the 1, while the methyl here would get the 3. Any questions on cycloalkanes and sort of numbers? All right. So let's talk a little bit more about alkanes and some of the properties. Natural gas, petroleum, a lot of those things are really just long chains of carbons and hydrogens together. They're non-polar. And the way that we do get things like gasoline and stuff is through a process which is known as fracking, which basically means we take these really long chains of oil and we basically break them into smaller chains like octane, which is 8, like your gas that you fill up in your car, broken down from a very long chain of carbons down to say like 8 carbons, and you get something like octane. Obviously, you can get some other sort of products by doing so. Now, because alkanes, as we talked about, are non-polar because they're essentially made up of carbon-carbon bonds and carbon-hydrogen bonds, which are all non-polar. They typically exhibit very weak intermolecular forces. So if you remember, our non-polar guys are going to be using dispersion forces as their main intermolecular force to basically interact with things. And that is essentially what nonpolar molecules will use. Those are those really weak temporary forces. And that's why we typically will see when we talk about melting points and boiling points, we usually will see low melting points and boiling points for alkanes, which means it doesn't take a lot of energy to melt them or boil them, because they're really only held together by these very weak temporary ones. A lot of the early alkanes, your methane, your propane, your butane, those are gases at room temperature, like you probably are familiar with, right? If you barbecue and all that kind of stuff. Larger ones are liquids. Alkanes are in that case insoluble in water. So they have very low solubility in water. Again, if you remember, in terms of solubility, that idea of like dissolves like. And as we talked about when we talked about those things, that means if you have something that is polar and polar, it's all good. If you have something that's ionic and polar, they will be soluble in each other. If you have something that is nonpolar and nonpolar, they also will be soluble in each other. You only run into a problem when you go kind of from nonpolar and you try to mix it with something that's polar. Those are going to be insoluble in each other. And that's what we get here with water, because water is polar. Alkanes are nonpolar. So really when you mix them, they do not mix. And what ends up happening is you see a layer where this is sort of your aqueous or water layer on the bottom, and usually your organic layer, which is your nonpolar guy, is usually that top layer that you see when you mix those guys together. Alkanes are also less dense than water, and that's again why you kind of see it float on top of water when you mix something. Also, maybe you've seen, if you've ever seen, obviously, a picture of like an oil tanker, for example, that leaked or crashed in the ocean. All the oil basically just floats on top of the water there. Again, because the oil being nonpolar and the water being polar, they really don't mix with each other. So in terms of boiling point here, the number of carbons in an alkane, the bigger the number of carbons that you have in an alkane, the higher the boiling point. And again, this has to do with your dispersion forces. If you remember when we talked about dispersion forces, the more carbons, for example, that you have, that means there's more electrons, and there's a greater chance that those electrons will move around and create that temporary separation of charge, which will allow it to interact. And this guy, which has less carbons, has less electrons as well, less of a chance of those electrons moving around and creating that temporary positive negative charge. So the hexane here would have a higher boiling point. The butane would have a lower boiling point. All three of these guys will all use dispersion forces, but the strength of dispersion forces increases with molecular mass or molar size or the number of atoms you have, because again, the more atoms that you have, the more electrons there are. So let's talk about a couple of important reactions here to finish up with alkanes. The one reaction that we've seen before is a typical combustion reaction. And in an organic combustion reaction, you have an organic molecule, which is basically carbons, hydrogens, and oxygens, plus O2. And when this occurs, it always makes CO2 plus water. So that is your classic organic combustion reaction. Usually a lot of times will liberate heat, sometimes a flame. This is essentially what happens when you go and you light your Bunsen burner, basically. Huh? You have some methane that comes out. You give it a spark. There's oxygen in the air. That spark basically ignites it, and thus you have flame. So a lot of those very first sort of organic guys, again, as we talked about, very flammable, usually will generate heat and fire, a lot of them. And this is your classic combustion reaction that we talked about, whatever chapter that was. We talked that one about when we talked about different types of reactions. And here's another example again here. This is a combustion reaction. This is a big organic molecule, but the essential part here is all carbons and hydrogens. Here's our O2, and again, CO2 and water are your classic combustion sort of products that you make. So pretty safe bet if you're asked to write an equation and it's starting with an organic compound and you're adding oxygen to it, you pretty much don't need to think about it. Just write CO2 and water on the product side, and you will have the correct equation that will occur here. Here's again our methane. Now, sometimes in most cases, when we talk about a combustion reaction, it's a complete combustion reaction. There is a combustion reaction, which is sometimes referred to as an incomplete combustion reaction. And really the only difference is you still have your organic guy, you still have your O2, you still have your water. The only difference is in an incomplete combustion, instead of CO2 carbon dioxide gas, you actually make carbon monoxide gas. So that is the only difference there, is that you would make CO. Again, it would have to be a very specific question for you to write CO on the right-hand side, and that would be the way it would be worded. I'm not planning on giving you that type of question, but in case in the book, if it happens to mention that it's an incomplete combustion, then instead of CO2 and water, you should put CO and water. But if it just says a combustion reaction, CO2 and water is definitely the products that would be made. Now, another reaction that occurs with an alkane is a type of reaction which is known as a substitution reaction. And in a substitution reaction, essentially what happens is pretty much what the name implies. Just draw something here. So if we have this alkane here, all drawn out, and we react it with something like an halogen, like Br2, Cl2, Br2, something like that. Sometimes you'll see HV sort of in there. Sometimes that's something like UV light or something like that. That's necessary as a catalyst to sort of get the reaction to go. So basically in a substitution reaction, it is pretty much like the name implies. In a substitution reaction, what you essentially get is something comes off. And then something goes on in that place. So what's going to go off in a substitution reaction with an alkane is a hydrogen. So hydrogen will go off, and a halogen will go on in its place. Yeah? So you basically get this switch. Now, if you look at this guy, you got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens to choose from. And in this case, they are all what are known as equivalent hydrogens, which means they're all the same, which technically means, if I could write, technically means that you could choose any hydrogen you like here and take it off. So I'm just going to take this one here because it's the closest. So he's going to go off. And one of these halogens here is going to go on in its place, like an off and on. And the first thing that you should learn when you try to draw products for these reactions is absolutely positively when you draw these products, there's only one small part of the molecule that changes. Everything else remains the same. People always want to do all kinds of weird things. They want to change the whole thing. There's only one place in all these sort of products that we're going to draw that changes. So what that means is you essentially can draw this guy all the way up to here exactly the same. Absolutely nothing changes. The nice thing about that is you almost have the answer given to you in the problem because you essentially just need to copy exactly what you got going on there. And this is the part that's hard for a lot of people because they figure, well, I got to change like thousands of things here, right? Something's happening. Now, obviously, I didn't draw this guy here because what he did is he went off. And this guy basically substituted for it, why it's called a substitution reaction. So what goes in that place where that hydrogen would be is the halogen that came on. Now, if you're keeping track of everything, we have a hydrogen that came off. And we also have a bromine that wasn't used. These two guys will also come together. And when they come together, you get HBr, hydrogen bromide. So you make this guy, which looks exactly the same, except that you took off a hydrogen, put on a bromine, and then the hydrogen that came off and the extra bromine that was there will come together and make your hydrogen bromide. And that is the basic reaction, except for a combustion reaction, that an alkane will go through. So why don't you try one here? Why don't you do this one here? And we'll do Cl2. All right, so take a moment and draw the product that you would get from this reaction. And why don't you try the one on the bottom I just did as well? Okay, so again, these also should be relatively quick to sort of draw because again, you have most of it there. As long as you don't try to do anything weird, like, make some weird bonds and stuff like that. So when we see this, we have our alkane. And again, we have our halogen. And we could rewrite our halogen if you want like this. And again, it's going to be a substitution reaction. You could choose any of those hydrogens that you like just to mix it up. I'm going to choose this hydrogen. So again, what's going to happen is a substitution reaction. That hydrogen is going to go off. One of these guys are going to go on in its place. And again, absolutely nothing else changes in the molecule on the left. So you essentially have what you need to draw right in front of you. You just draw it exactly like you see it. Don't do anything weird. Don't reinvent the wheel. Draw exactly what it shows there. Obviously, the thing that you would not draw is the guy that's coming off. But in its place, you put the guy that is coming on, which in this case would be our Cl. Same thing's going to happen. That H comes off, and that other H, that other Cl will come together, and we will get hydrogen chloride as well as our product. Again, you could choose any hydrogen you want, take one off, and put one of those chlorines on. Any questions on that one? Same thing down here, our Br2. This is our cyclopentane. So remember that each of these are carbons. And at each of these carbons in cyclopentane, there actually is two hydrogens. I won't draw them on each of them, but at every single point here, because there's only two lines coming in, there are two hydrogens at each of those spots. So again, I won't draw them all, but they all have two hydrogens. So same thing is going to happen here. One of these guys, don't matter which one you choose, is going to go off. And one of these guys is going to come in its place. Nothing weird happens here. Like this ring does not magically open up or anything like that. It looks the same, really crappily drawn there, but it looks exactly the same. You still even have that one hydrogen. If I didn't hit the button there, you still have that one hydrogen that didn't change. The only difference is you're going to put that Br on the same carbon where that hydrogen came off. Same thing, the hydrogen that came off is going to hook up with our bromine, and we will get HBr in this case. So again, don't do anything weird, don't do anything funny, don't break these rings into separate structures. This is not 6 carbons. Let's draw a straighter line going that way. It should only be, again, be 5 carbons. Grab my eraser, maybe get rid of that part of it. There we go. Looks a little bit better. So when we look at these, although we had a choice of a lot of hydrogens to take off and put that halogen in its place, typically when you do this, you are sometimes asked to draw what is known as the mono-substituted product. And that's what we did. Mono-substituted means we just put one halogen on. Mono-substituted, we just replace one. Mono-substituted, we just replace one. In reality, at some point, if you let this reaction continue, every single hydrogen will get replaced with the halogen. But usually in a book problem or a test problem, or probably even in a lab, they oftentimes will ask you to write the mono-substituted product. That again just means take off just one hydrogen and replace it with one halogen. Any questions on this reaction here that halogens undergo, or alkanes undergo? This is sometimes what is referred to as a halogenation reaction, because that's basically group 7, right, is what you're putting on. And group 7 on the periodic table are our halogens, right? So when we put our Br on, they were put in a halogen on, and it's sometimes referred to as a halogenation reaction. Here, same deal. We're going to take one of these hydrogens off. One of these bromines will go on, and that is where we get our bromine that's attached. Again, you can see this ring right here and this ring exactly the same. Didn't open up, didn't do anything weird. And then again, that H that came off will connect with that Br to get you the HBr. So a combustion reaction for our alkanes, CO2 and water, and a halogenation reaction, which is what is referred to as a substitution reaction, where you take off a hydrogen and put a halogen on. Mono-substituted is usually what you have to do. Any questions on any of that there? That should be chapter 10, I think. Yep, it is. All right, so we are then going to go on to chapter 11. So let me go find that real quick. Got that somewhere, I think. Maybe. Let's do that. Let's do this. Let's do that. Go with that. Still doesn't like that. Let's try that again here. Okay, let's try that one. There you go. Give it the college try there. All right. All right, so in this chapter here, we're going to talk about alkanes, or alkenes, I'm sorry. And these alkenes, hang on one sec here. Try that one. Technology, hang on here. That one. There we go. Found it. All right. All right. So in chapter 12, we're going to talk about alkenes and alkynes. And again, alkenes, functional group is that carbon-carbon double bond, while alkynes have a carbon-carbon triple bond as the functional group. And these are what it is we will talk about are what are known as unsaturated hydrocarbons. They're unsaturated hydrocarbons because they have at least a double bond or a triple bond, which, as we talked about, every time you put a double bond or triple bond on there or an extra bond, you lose hydrogens, right? So you lose 2 hydrogens for every bond. And if you remember alkanes, which are what we just talked about, are carbon-carbon single bond. These are what are sometimes referred to as saturated hydrocarbons, which essentially means that it has the maximum number of hydrogens that each carbon can have. And again, as we put on another bond, say a double bond between the 2 carbons, as you look from the top there here to our bottom, we have lost again 2 hydrogens, 1 on each carbon, to make that bond that basically comes in. So that's why these are referred to as unsaturated hydrocarbons, because of that. So let's start with alkenes. Again, the functional group for an alkene is that carbon-carbon double bond. It needs to at least have 1 of those. It has a general formula, as you see on the bottom there, of CN2N. And again, the difference between that and our alkane, which is CnH2n plus 2. We again lose those extra 2 hydrogens as we make that double bond here. So it's just CnH2n like that. We don't have the plus 2 on this as we go from our alkane to our alkene. Now, in terms of how we name these guys and so forth, they are as well based off of those first 10 alkanes. So for example, if we look at this guy, this is 1 and 2 carbons, and 2 carbons is based off of ethane, and alkenes is what this is because it has a double bond, and that ends in ene. So although this is a common name, we would call this ethene, ene. Ethene, basically, ene, telling us that it has a double bond. Because of that double bond, as sort of talking about sort of geometry of it as well, because of that double bond, if we count it, this carbon here has 1, 2, and 3 electron pairs. And it also has 1, 2, and 3 bonds. And unlike alkanes, which has that tetrahedral geometry, our alkenes with the double bond, because of that double bond, gives us that trigonal planar geometry, which again, a reminder, is the one that kind of makes a triangle. Yeah, so trigonal planar, right? So it gives us that triangle sort of geometry, bond angle about 120 degrees. So if you were drawing these things, for example, for lab, it should have sort of a different angle than the alkanes, which have that tetrahedral angle of 109.5. Again, for us, you do not have to draw any of these things with angles or anything like that. Alkynes is the next group of organic guys, which again, the functional group here is our carbon-carbon triple bond is our functional group. And it has a general formula of CnH2n minus 2. And that is because we made not 1 bond, but 2 more bonds from our alkane, which means, again, our alkane had the plus 2 hydrogens. Our double bond, we lost those 2. And now our triple bond, we have to take even more off. So it's actually minus 2. And that's what we see here. There's 2 carbons. 2 times 2 is 4. Minus 2 gives us 2 hydrogens here. This is a common name. If we were to name this, it also is based off of the alkanes. It has 2 carbons, which again is based off of ethane. But because this has the carbon-carbon triple bond, It's an alkyne, which ends in YNE. So this becomes ethyne, YNE would be the correct IUPAC way of naming it. Again, acetylene is sort of a common name for it. Also, because of this triple bond, this carbon here ends up with 1 electron pair, 2 electron pairs, and also 1 bond and 2 bonds. And it also has a different geometry than alkenes and alkanes. Its geometry, as it says over there, is linear. So it has a 180 degrees. It's basically a straight line as you go across. And it would have obviously a different sort of geometry as well. So these double bonds and triple bonds cause different geometries in these organic molecules. In addition, it also will cause these guys not to be able to freely rotate because of the double bond or triple bond. So when you have an alkane, like we were talking about in the previous chapter, and you have just carbon-carbon single bonds, this carbon and this carbon, it's free to basically rotate around that bond in any way. And that's why when we were talking about earlier, somebody was asking, can I draw the BR on the bottom? Can I draw it on top? Does it matter? And with an alkane, it really doesn't matter because there is that free rotation around that single bond. So even if you draw it up, it could just rotate around and go to the bottom, and it's basically the same thing. But once you slap a double bond in there or even a triple bond, it basically locks these carbons into place and you lose that rotation that the alkanes have. So it's not able to really freely rotate around in sort of three-dimensional space because of the double bond and triple bond kind of lock them into place. And that creates certain types of isomers that we'll talk about in this chapter that we don't necessarily see in the same aspect in alkanes. We'll talk a little bit about sort of the properties here. Alkenes and alkynes, they're still nonpolar. They still are basically made up of carbons bound to carbons, carbons bound to hydrogens. So even though they have double bonds or triple bonds, they're still very much like the alkanes in that sense because they have just those nonpolar bonds. So they also will have low melting points and boiling points because of that. They are still going to be using those dispersion forces just like our alkanes. They also are nonpolar, so not so good with water, which is polar, right? So that polar, nonpolar interaction, not going to be really good when they come together. As I mentioned before, alkenes and alkynes, they're considered unsaturated. Again, as you put on that double bond and that triple bond, so as we go from our alkane, which is all single bonds, to our alkene where we have one double bond, you can see we've lost 2 hydrogens, to our alkyne, which has lost another 2 hydrogens as we put on that third bond. So 2 hydrogens gone as we go this way, another 2 hydrogens gone as we go this way. And again, every time you put on a bond, you've got to lose 2 hydrogens. Again, really the basic idea of that is to allow room so carbon doesn't end up with, again, too many bonds, more than 4 bonds. And as I mentioned before, in terms of how we name them, they're basically named like their classes. So again, alkene ends in ENE. So basically you take the alkane name, drop the ANE, and put the ENE at the end of it. Alkynes end in YNE. Same idea. You take the alkane name, basically, drop it, and substitute in these guys, depending on whether you have sort of a double bond or a triple bond when you do it. And again, we draw the condensed formula very similar. You could draw it either way, this way. You could draw it like this. Again, if you see this sort of connection written like this, the connection is like what you see over here on the left. Although sometimes people think when they see this as the hydrogen attached to the carbon, it's actually not. It's still the carbon attached to the carbon, attached to the carbon, and then the hydrogens attached to those. So this is essentially what we're looking at there. And in condensed form, excuse me, sometimes people will get that a little bit confused. So let's talk about how we name these guys. And surprisingly enough, like I said, it's pretty much the same deal as how we name alkanes. So when we go to name these guys, just like we did with everything else, the very first thing that you want to do is figure out the longest continuous carbon chain. So we're still looking for the longest carbon chain. The important part, though, when you do an alkene or an alkane is that longest carbon chain has to have the double bond or the triple bond in it. So it's got to have the double bond or the triple bond in it when you're counting it. So for example, on this one, if you went 1, 2, and 3, that would not work because you ignored the double bond altogether. So if we count this, we have 1, 2, 3, and 4 carbons going that way. We also would have 1, 2, 3, and 4 carbons going that way. And that means that no matter which way you go, you are going to end up with 4 carbons. And just like before, we would go with 4 carbons, and that would tell us that it is based off of 4 carbons, and that is going to be based off of butane. But when we look at this, it is a double bond, which means that this is an alkene. So our butane goes from butane to butene, E-N-E, again for the double bond that is there. Now, just like before, we're going to kind of highlight our longest continuous carbon chain. We also still see that we have a group attached, and this is a methyl group, right? Just like what we had before. We want to come to the numbering, and this is important when you're numbering with anything that has a double bond or a triple bond. We can number 1, 2, 3, and 4, or we could number 1, 2, 3, and 4. Again, we want to go with the lowest number. Now you may say to yourself, okay, my methyl group is at carbon number 2 as I go in the green direction, while if I went in the red direction, my methyl group is at carbon number 3. So you may say to yourself, I want to number the green way because that gives me the methyl group at the lower number. We are looking for the lower number, but when you start dealing with double bonds or triple bonds, the lower number needs to go to the double bond or the triple bond. So you want a number whichever way will give not the groups attached. The double bond or the triple bond gets the priority in terms of numbering. So that's something that's slightly different. Regardless of the groups, we want to go whichever way will give our double bond or triple bond the smaller number. So going in the green direction, it would give our double bond carbon number 3, while actually going in the red direction, our double bond would be at carbon number 1. And that's what we would actually include into our name. This would be known as 1-butene. The 1 is for the location of the double bond. I guess if I didn't use the same color, that would have been probably a better move. Let's see if I can just shuffle a little bit of that out. There we go. So the 1 here, again, is for the location of where you find the double bond. So when you have more than one option as to where that double bond or triple bond would be, you do need to give a number. So in this case, the double bond is here. It could have been here at carbon like 2 and 3. It could have been here between 3 and 4. Because there's multiple options of where that double bond is located, that is what this number refers to. Again, the double bond location. Now, the rest of it is just like normal. Since we had to go this way in terms of numbering because of the double bond, we still have to stick with that way of numbering. So that means that our methyl group should end up at carbon number 3, and this would be 3-methyl dash 1-butene. 3-methyl because at carbon number 3 from the double bond direction, we have a methyl group. 1-butene because the carbon-carbon double bond is at carbon number 1. Any questions on that? So let's take a look at this one. Here we have a triple bond, and that triple bond is going to tell us that this is an alkyne, YNE. We want to find our longest carbon chain that has the triple bond. So that's 1, 2, 3, 4, 5, and 6 if we go straight. That's 1, 2, 3, 4, 5, and 6 if we go upwards, kind of straight and then up. And that looks like the same. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Again, might as well take the straightest 6. 6 carbons here going to be based off of hexane. So going this way is hexane. It has a triple bond, so hexane becomes hexyne. I'll get to your question in just 1 second. And since that is hexyne, we also have a group that's attached to it. This is a 2-carbon group, and that is a ethyl group. Now we want a number. We could number left to right, or this would be 1, 2, 3, 4, 5, and 6. Or we could go right to left, which is 1. I guess you should number the carbon. 1, 2, 3, 4, 5, and 6. Again, going right to left gives us the triple bond at carbon number 2 versus carbon number 4. So in this case, we do want to go right to left, which is going to give us our triple bond, the smaller number. So this would be, and what I'll do is I'll renumber it here real quick. Get rid of these guys here. We'll renumber it this purple way. So the way we would want to go is numbering it then this purple way, which means that this is carbon number 1, this is carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6. That means at 3 hexyne, 3 for the triple bond. And now because we had to go this way with the purple for our numbering, our group is now at carbon number 4 here. And that means at carbon number 4, we have an ethyl group. So this would be 4-ethyl for the carbon at the ethyl group at carbon number 4, where that triple bond is, going in that direction. 3 hexyne, the 3 for the triple bond location. Any questions on that there? So again, just to reiterate why we chose numbering for both of these, we ended up numbering the guy on the left in this direction because the double bond is the smaller number going in that direction. Our double bond on the left here would be at carbon number 1. If we went in the green direction for this first one, our double bond would be at carbon number 3. So again, it's as simple as 1 is less than 3. Yeah? So we always want to go with the 1 in this case that will give the double bond or the triple bond the smaller number. And that's the same reason here why we went in this direction on the right-hand side, again, going from right to left in terms of numbering the carbon. That gives us a triple bond at carbon number 2 versus a triple bond at carbon number 4 if we went the other way. And again, 4 being larger than the 2, that's why we want to go that way. Once again, once you choose which direction you're going to number, because of the double bond or the triple bond, you are locked into that numbering position for the groups that are attached. So you can't number both directions. Once you lock yourself in, like we did on the left-hand side, we were locked in going in this direction. That means when we got to our methyl group, we were locked into the number of 3 for its location. Same thing once we locked in going in this direction, because of the triple bond, we were locked into number 4 being there for our ethyl group. Again, once you lock yourself into the numbering direction based on the double bond or the triple bond, you got to keep it for everybody else that's on there. Any questions on that there? Okay, so I guess we will wrap up then lecture here, I think. Looks like the right time. And again, we'll take 15 minutes or so and we'll take a little break. Hang on real quick, just try to answer your question. You're right. You're correct. Thank you very much. This one actually should be, thank you for noticing that. I'll learn to count. This actually should be, it should be 2 hexyne. Thank you for catching that. I'll do the classic. I was just making sure somebody was paying attention, but no, it actually should be 2. It should be 2 hexyne. Yeah. Thank you very much. Yeah, you would want to take the first carbon where that triple bond is, and it would be 2 in this case. Everybody else should be okay, I think, 4. Just like over here, we took the first carbon where that's at, which would be 1. Thank you very much. Any other questions on that? Yeah, so that one on the right, again, make sure you change it if you didn't. It should be actually be 4 ethyl, 2 hexyne, and one of these days I'll learn to count, I think, maybe. Yeah. All right. Any other questions on this? So we'll take a break, and again, we'll discussion. If you have some questions, we're transitioning here through chapter 12, it looks like, or 11, which is alkenes. And again, we'll hopefully get through most of it on Wednesday as well. And the next day or so, in terms of your exam scores should hopefully be up there on Canvas. Just so you know, when I do probably release the exam scores, it will just be your exam scores that's been updated. Need just a little bit more time to update everything else with your lab grade and stuff like that. But my goal is the next day or day-ish, you should at least be able to see your exam. When you do see your exam, you'll be able to see hopefully both files. You'll be able to see what you uploaded and also the exam as well. And there'll be like a feedback file where there'll be some markings and stuff like that, where you can kind of see, what was marked wrong on the written part and stuff like that. So keep a lookout on that for the next day or so. It should hopefully be up there. But like I said, once that perhaps gets updated, that may not necessarily mean that your overall grade is correctly updated yet, because I still need to take your current lab one that I think I got last week and kind of put that in there with your homework and stuff like that. So just, keep that in mind. It will probably come in stages this week, your exam score, followed by later in the week, probably your updated sort of overall grade as well. Any questions on any of that stuff? Okay, so again, take a 15-minute break, and then if you do have questions, feel free to come back. If not, then I will see you on Wednesday when we will continue.